We have a lot of important information to go over in section 4.4 here. What we're going to start with in this video is we're going to focus on looking at something called the first derivative test. And that's going to kind of bring together a lot of things that we've already touched on, including ending the last section with that corollary to the mean value theorem, which was a way to prove that where a derivative is positive, the function is increasing, and where the derivative is negative, the function's decreasing. So first, what we're going to do is we're going to pull together some of the things that we have already learned from the last couple of sections, and we're going to pull all that together and sort of culminate with this first derivative test. So from 4.2, here's what we know. We know that relative or local extrema occur at points where the derivative f prime is either equal to 0 or where the derivative does not exist. Now, because that's where, local extrema occur, we say these are critical numbers. These are critical points on the function. So, first of all, notice that language. These are critical numbers. They are points. They have to be a critical point, you have to first be a point. So you have to be in the domain of f. And again, critical numbers are defined to be these locations where the derivative is either equal to 0 or does not exist. Now, why don't we just say these are local extrema? Well, that's because not all critical numbers are local extrema. So remember, think about the example that we looked at with the y equals x cubed graph. So if you're looking at the function y equals x cubed, we have a horizontal tangent line here at x equals 0. So we have a critical point at x equals 0 where the slope of the tangent line, so a location where the derivative y prime is equal to 0 here at x equals 0. Okay, but that is not the location of a local extrema. So not every critical point is going to be a relative extrema. And so that's why we call them critical numbers, and then we investigate further to decide if in fact we might have an extrema. Now, from the corollary to the mean value theorem at the end of section 4.3, we learned something pretty intuitive, even without that mean value theorem kind of approach to the proof, which is f is increasing when its derivative, f prime, is greater than 0. So if the rate of change is positive, the function is increasing. F is decreasing when its rate of change, its derivative, is negative. So let's pull this together and kind of just observe some examples here. All right, so first of all, let's take a look at these critical numbers. So our critical numbers are these points on f where either f prime is equal to 0 or where f prime does not exist. So f prime is equal to 0 at b, at c, and at d, and f prime does not exist at a. So we have 4 critical numbers. Now notice in this situation though, the extrema, so if we were to talk about which ones are actually extrema, then it's a different story, right? Oops, I just dropped my pencil and what I was doing there, sorry about that. So our relative or local extrema in this example, well, there is one here at, well, that's kind of a weird way to show it. Let's maybe down here, let's circle it around. X equals A is a local max. X equals B is the location of a local min. But f prime of c is equal to 0. There's that example again. It's neither a min nor a max. At x equals d, we also have a local max. All right, so that's kind of the observations from 4.2. Okay, now let's go ahead and kind of look here at where f prime is increasing is going to be where f prime is greater than 0. So all these locations where f prime is greater than 0, this is where we are increasing. So we can see all these intervals where the rate of change or the derivative is positive. These are all intervals where the function is increasing. And then lastly, where the function is decreasing is where the derivative or the rate of change is negative. So we are decreasing in all of these intervals where f prime is, and there is a typo in this last part of this picture that I used from the internet here. So this last one right here, this should not be an f prime greater than 0. This is a region where f prime is less than 0. So change that if you would please. This should be a location where f prime is less than 0. So that's our last kind of region there of decrease. All right, well, let's pull all of these observations together, and this culminates in something we call the first derivative test, and it's going to help us find where a function is increasing, decreasing, and the extrema. So we're going to, relative extrema, we're going to pull all of this together. All right, so essentially what we're going to do, so the theorem is formally stated there in that box. It's directly from your book here. So let's kind of move down. We're going to summarize it kind of in our own steps here. So first we're going to find those critical points. So that's exactly kind of what's highlighted in, highlighted in yellow up above. So all of those critical points are our locations where the derivative, so where f prime is equal to 0 or where f prime does not exist. And then let's take a look at, I'll say this sign analysis we're going to do. We're going to say, for example, this is obviously not always going to be the case. We're going to kind of use the graph up above. So let's say we found those points A, B, C, and D. So those are the points that we found for our critical numbers. So suppose we found A, B, C, and D. Now what we're going to do is we're going to, this is a lot like the example we did at the end of the last section, we are going to perform sign analysis, and we are going to sub some numbers into f prime and decide if what we get is positive or negative, and that is going to tell us on the original function if we are increasing or decreasing. Okay, so that's what we're doing here. So, we pick any kind of number, and that's, we're going to see how this is going to work in some concrete examples later. But let's kind of scroll back up. So suppose we pick something before A. If we were to sub in some value here, that is where, in our above example, that is where f prime was positive. So if we were to sub in something there, we would find out that f prime is positive, and that is going to allow us to conclude that that is where f is increasing. Then if we subbed in a value in between A and B, and we find out that in fact f prime is negative, that is going to allow us to conclude that f is decreasing. And again, suppose we plug in a value into f prime, we find out we're positive, so once again that allows us to conclude that we're increasing. But what we don't want to fall into this trap of thinking that these will always alternate, because they won't. So suppose between C and D we're still positive, like the above graph, and so we're still increasing. And then suppose lastly we change back to f prime being negative, and so we are now decreasing. So what this, again, be looking at your graph in your notes, so that's this graph right here. So this is all reflective of that example. So let's actually, we'll just leave that there. Okay. And so then the last part of the observation, obviously we have all of our increasing and decreasing intervals, but now what we want to be able to write out is at these x locations where we had critical points, we want to think about which ones are actually extrema. So if I change from increasing to decreasing, that is going to tell me I am going to have a local or relative max at, and then, it would be at the value A, and to figure out the actual max value, you would sub that back into the original function. Now, if we change from decreasing to increasing, that is going to tell us that we are going to have a local minimum at, again, x equals b, and to actually find that min value, you sub it back into the original function. Now, in this case, what we have on x equals c, I'm just going to leave that one blank. Even look back up at the graph. That was not a min or a max. It kind of flattens out. We have a horizontal tangent line, but it kept increasing. So it is not a relative extrema. And then we would end in this example, we would end with going from increasing to decreasing around x equals d. So we would end with another local maximum. Again, at the x value of d, sub that back into the original function to actually figure out what that local max is. All right, so this is going to be the process. When we come back next time, we will get into some examples.